Hello, everybody. My name is Wolf Geppert. I am the chair of the European Astrobiology Institute, and it is my great pleasure to welcome Bertram Bitsch for today's lecture. Bertram did his PhD at the University of Tübingen in Germany in 2011 and then 2011, and then he spent his 2 years of a postdoc at the University Côte d'Azur. And then he went to do a 3 years senior researcher position in the University of Lund in Sweden from 2014 to 2017. And now he is working at the Max Planck Institute for Astronomy in Heidelberg in Germany, which is one of our participating institutions. So I will now finish my introduction and get over the word to Bertram Bitsch, who will be giving his lecture now. Welcome again, and welcome to you all. Many thanks for joining.
Yes, thank you very much for the invitation. I will share my screen and presentation now. I assume you can see the presentation. So I will talk to you about the importance of water for planet formation. And I would like to present you first the outline of my talk, where the idea is here to show how does water actually influence planet formation. For that, I would first like to give an introduction about exoplanet observations and a little bit of exoplanet statistics. So basically to see how we can actually compare our formation scenarios to observations. I will then talk a little bit about the general formation scenario that we use within these models, then talk about the formation of super-Earths and their composition. And I will then, towards the end of my talk, actually show how how other planets in the system, in this case giant planets, can actually influence the composition of inner planets. And also, I would like to point a little bit about what the stellar composition might actually be able to tell us about planet compositions. So to start my talk, I would first quickly mention the main methods to detect exoplanets. As you probably know, one of the main methods is the radial velocity detection method, where the idea is that an unseen planet tugs along the star, and you basically shift the light either in the blue or in red, and you can then basically detect an unseen companion. Actually, the first exoplanet detected around the main signal score actually happened with this radial velocity method. The other main method is the transit method, where you basically just observe a dip in the brightness curve as a function of time when a planet basically moves in front of the star. This method actually gives you the radius of the planet. So basically, if you combine both methods, the radial velocity method that can actually determine the mass of the planet, and the transiting method, you get mass and radius, and with that you can actually start to run interior structure models, because you can calculate the mean density of the planet. So if you have both a mass and radius measurement, you can do many more things than, of course, if you only have one of those measurements. The exoplanets, there have been a lot of exoplanets detected. You see here a plot that is already a few years old, but that still illustrates the point that I would like to make. In this plot, you have the planetary mass against the orbital distance in AU, and the colorful dots represent exoplanets, so planets around other stars, while the black dots represent the planets around our own solar system, except for Mercury and Mars, which are actually not massive enough to be in this plot, which already shows you that, of course, there's a bias from the exoplanet observations towards detecting only more mass-rich planets. Within this plot, you can identify three main groups of planets. One is the cold Jupiter planet, similar to our own Jupiter. Another group is the hot Jupiter planets, so planets in mass similar to Jupiter, but orbiting very close to their central star, where it's very hot. And another group is the so-called group of super-Earths, or sub-Neptunes, mini-Neptunes planets of a few times the mass of the Earth, where we will discuss a lot in this talk on also about the composition of those planets. From this plot, it actually seems that these giant planets are actually in the majority, but this is also a detection bias, because it's easier to detect more massive planets compared to lower massive planets. So in reality, actually, these smaller planets are the majority of planets in our own galaxy. I would also like to point to the diversity of planetary systems that we observe. I've plotted here 5 different planetary systems. The top, of course, is our own solar system, where the arrow bars mark the aphelion, perihelion of the planet, so basically a measurement of the eccentricities of those planets. And what you see here, that most of the exoplanetary systems that we actually observe, they're very close in, they're very compact towards their host star. You see, most of the planets are within 1 astronomical unit. And maybe this Kepler 90 system is actually like you could think of it like a squeezed version of the solar system, where actually the radius of the dots that I marked here is a measurement of the planetary mass. So basically you see here you have 2 Jupiter-like planets around 1 AU, and then an inner chain of smaller planets. Very interesting, in my opinion, from a formation perspective, is also the WASP-47 planetary system, where you have 2 smaller Neptune-sized planets and the gas giant orbiting in the middle, and then outer eccentric gas giant, which really tells you there's a lot of different things going on in this system. The reason why I plotted this very unspectacular Kepler-21 system is actually that the majority of planets that we actually found are in systems like Kepler-21, where you mostly see actually only 1 transiting planet. However, this does not mean that the system only contains 1 planet, because if the planets have mutual inclinations to each other, you might actually not see all the planets. And we'll come back to that point later on. Furthermore, in these systems of super-Earth planets, as I said, 1 out of 3 solar-type stars should actually host a super-Earth within a 100-day period. So this is actually a very large abundance of these systems. We can now take a closer look into the configuration of these planets. You see here on the left a plot where we plot the period ratios between planetary pairs. So basically, how often does the outer planet orbit versus the inner planet. And you see here marked 3 prominent resonances, so the 2-to-1, 3-to-2, and 4-to-3 resonance. So the 2-to-1 resonance means the inner planet goes 2 times around the star, while the outer planet goes around once. And what you see here in the distribution of the planetary pairs of the exoplanets is actually that most of the planetary systems are actually not in a resonant configuration. And this is actually poses a sort of question, because when planets start to grow and also migrate through the protoplanetary disk, you would normally pile them up in resonance. But this is apparently not the end product of the planetary systems that we observe. Additionally, if we look within the same planetary systems, it actually seems that planets within the systems actually have similar sizes of masses. In this plot here, you see here different a sample of Kepler planetary systems. We also have here the solar system with the terrestrial planets in the solar system. If you look within each system by its own, you actually could identify that the planets within the system actually have similar sizes and probably also similar masses. And this is also a constraint that we have to match from our planet formation simulations. Of course, the planetary masses from this system to system differ. You see this here. The system down here has smaller planets than for example, this system. But within the same system, it seems that the planets have similar sizes and similar masses. And this gives, as I said, another constraint we have to match in our planet formation simulations. Now, in the planet formation scenario that we follow for these simulations, the so-called core accretion scenario, where we start off with a star that is surrounded by a protoplanetary disk consisting of dust and gas, where the dust contribution is around 1% of the total mass. In there, you have the small micrometer-sized dust grains that can grow by coagulation or by condensation to millimeter, centimeter-sized pebbles. These pebbles can then form planetesimals by a gravitational collapse of a pebble cloud to form planetesimals, typically of several 10 to 100 kilometers in size. Now, these planetesimals and pebbles can actually start to form planets by accretion. You can either accrete planetesimals, or you can accrete the small millimeter, centimeter-sized pebbles in the so-called pebble accretion scenario. Depending how fast you can actually accrete material, you can either form terrestrial planets, or you can also form gas giants if you form a planetary core that is several Earth masses within the lifetime of the disk of a few million years. Now, the planet in itself actually gravitationally interacts with the gas disk. You see here a plot from a simulation where we show the gas surface density. You see here our tiny planet and how it exerts a spiral wave in the protoplanetary disk, and the planet exchanges through the spiral wave angular momentum with the protoplanetary disk and migrates through the disk. If you have a larger planet like a Jupiter mass planet, it actually opens a gap in the protoplanetary disk because it pushes away angular momentum from its orbits and opens this deep gap in the protoplanetary disk. Then, at the same time, you have to take into account the disk evolution. So the disk evolves in time over several million years. Then, at the end of our simulations, we actually have to compare the masses and the positions of our planets with the observed planet populations. We furthermore can then compare directly to the super Earth populations to take a look into the systems. We can also look at the giant planet population, and we have to take care of the composition of those planets as well. So, for example, are they made out of rock or are they made out of water ice? And this, of course, is a lot of different questions that we have to answer within these simulations. And the process, of course, is very complicated, so we'll just outline here a few of the processes that we actually take into account here. So first, I would like to mention the radial drift of the small pebbles that we have in the protoplanetary disk. So the idea here is, or basically the physical process is that the disk is hotter and denser, close to the central star, so you actually have a radial pressure gradient in the protoplanetary disk. And this actually mimics a decreased gravity acting on the gas. So the gas in the protoplanetary disk actually orbits slower than the Keplerian velocity. You see this here in the equation. So the gas velocity is slower than the Keplerian velocity by this defined by this parameter eta, which depends on the disk's aspect ratio and is also a function of the disk local pressure gradient, of the radial pressure gradient. The particles, on the other hand, so the dust and pebble particles, do not feel this pressure gradient and want to orbit on a Keplerian force. This actually means they feel a headwind from the sub-Keplerian gas, which drains the angular momentum from the particles, so they actually spiral inwards through the disk. So the pebbles drift and move through the protoplanetary disk. We can actually make use of this to actually build planets, and this is what happens in the so-called pebble accretion scenario that you see illustrated here in these two cartoons. So you have here our inner protoplanet, and you see here a planetesimal or a pebble coming in. The planetesimal will actually mostly be scattered away because it needs to come very, very close to the protoplanet to actually be accreted. The pebble, on the other hand, it drifts inwards, but then it actually can spiral on towards the protoplanet. And this is because the pebble loses the angular momentum due to the friction with the gas. So the same process that makes the pebble drift through the disk is actually also responsible for the pebble to lose enough angular momentum when it enters within the planetary Hill sphere to be accreted onto the planet. The accretion rate of the planet given by this equation depends on several parameters. One is the Stokes number of the particle, which is basically a measurement of the size of the particle. So the larger the particles, the easier it is to accrete. Then it depends on the Hill radius of the planet, which basically is a measurement of the mass of the planet. So the more massive your planet is, the more pebbles you can accrete. Depends on the Keplerian rotation, and it also depends on the pebble surface density. So basically, the more pebbles you have available, the more pebbles you can accrete. In most models, the pebble surface density is actually proportional to the square root of the flux of the pebble, so how many pebbles drift through the protoplanetary disk. A pebble accretion becomes efficient mostly once the planet has reached a mass around the mass of the moon, so 0.1% the mass of the Earth. However, planetesimals, when they normally form, are initially actually a bit smaller than this mass, so you might actually need some initial collisions before pebble accretion can actually finish the job of going all the way to planets of several Earth masses and beyond. Now, pebble accretion actually stops at some point. This is at the so-called pebble isolation mass. The idea here is that the planet starts to open a partial gap in the protoplanetary disk. You see here in the plot on the left, the planet here sitting at 1, and you have an azimuthal distribution of the gas. So you have the full 2 pi annulus of the disk, and the color coding gives you the density perturbations of the planet. You see the planet opens a small partial gap in the protoplanetary disk, And this is because the planet pushes away the material around its orbit, so it actually gives angular momentum to the protoplanetary disk. And this actually has an influence on the velocities of the gas, as you see here on the plot on the right, where we plot here the azimuthal gas velocity divided by the Keplerian velocity as a function of orbital distance. You see in the outer regions of the protoplanetary disk, where the planet has no influence, the gas has the sub-Keplerian velocity, so the pebbles would drift inwards, as I explained before. But close to the planet, you see that the gas is accelerated to super-Keplerian velocities. This actually means as the pebbles drift in from the outer disk, they would actually, here in this case, in this region, be accelerated by the gas, and they would stop their inward movement and would be accumulating in this trap exterior to the planet. And this means if the pebbles accumulate exterior to the planet, they cannot be accreted onto the planet anymore. So the pebble accretion actually self-terminates once the planet reaches a critical mass. This pebble isolation mass is a strong function of the protoplanetary disk parameter, so it depends on the disk aspect ratio, the viscosity of the disk, the radial pressure gradient in the disk, and depends also on the Stokes number, so on the sizes of the particles, where particles with larger sizes can be trapped easier compared to particles with smaller sizes. So the same effect of the pebble isolation mass is actually responsible or could be responsible to explain the rings in these beautiful ALMA observations that we have. So you see here a protoplanetary disk observations. You see rings and gaps in this disk. And if a planet would be located in this gap in the pebble distribution, it could actually explain the observations. Of course, not all gaps in protoplanetary disks are necessarily caused by planets, and there are other observation effects that could explain the structure of these protoplanetary disks. However, planets are one of the explanation of these structures. Now, equipped with these tools, we can actually take a look at the formation of super-Earths. So the first thing that I would like to mention here is actually the evolution of the protoplanetary disk, because the disks evolve in time. And especially the temperature evolves in time as the disk becomes older. You see here a plot where we have the temperature as a function of orbital distance. And we have here 4 different times of the time evolution of the protoplanetary disk. So we start with this slightly blue curve, and we arrive at the black temperature distribution after 3 million years. The blue band here gives you the water-ice line transition. So if you're in the cold part of the disk, you have icy particles, so that can actually lead to enhanced growth. And in the warm regions of the disk, you do not have icy particles anymore. You have a reduced growth because the particles might actually be smaller. We have to take this effect into account when we look at the formation of planets. And for this, I would like to show you a video now for the formation of planets in these simulations. So what you have here is first the planetary mass on the y-axis against the semi-major axis. In the movie, you will see our planets here as they will grow and migrate through the disk. The color coding of these planets will give you an information about the water content of these planets, where red would be rocky planets and blue would be icy particles. You have here in blue the water ice lens that divides the 2 reservoirs. These gray lines correspond to regions of outward migration. So if a planet is located here, it can actually migrate outwards, and if it's located exterior to this region, it can migrate inwards. And this dashed line corresponds to the before mentioned pebble isolation mass, which is the mass to which the planet can actually grow by pure pebble accretion. So I will play the video now that you can see here. So you see here the planets smoothly growing by pebble accretion. They get stuck in this region of outward migration, and they slowly start to migrate in. They actually form a chain of small planets here that migrate all the way towards the inner region of the protoplanetary disk. You see here you have also during the gas phase some collisions of the planets as the disk evolves. I will play the movie again. We can again also focus here first on the planets in the very outer region of the disk. You see they grow actually a bit slower than the planets in the slightly inner regions of the disk, and this is because pebble accretion is more efficient as you move closer in, because the pebble surface density is larger. And as the disk evolves, also the ice line moves in, and the region of outward migration changes, and you basically move your system into the inner region. What you see here in the very end is that you have a compact configuration of many super Earth systems. We now have to compare this to the. We can take a look at the dynamics of these simulations a bit in more detail, where we have plot here the semi-major axis, the eccentricity, the inclination, and the masses of these planets as function of time. The gray vertical line here marks the dispersal of the gas disk phase. So in the so during the gas disk phase, you have pebble accretion, you have planet migration, but when the gas disk dissipates, you only have the n-body interactions between the bodies left, which of course also act during the gas phase. We mark here in different colors different planets. So in gray are the planets that actually are far away from the central star, that we could actually not observe with Kepler because they're just too far away. In color, we actually mark the planets that survive up until 50 million years. So what you see first is that the planets start to the masses increase smoothly, and this is because of pebble accretion. Then at some point the growth stops, and this is when the planet reaches the pebble isolation mass, so it stops accreting pebbles and the mass stays constant. Then here these jumps in the diagram correspond to collisions between the planets that can lead to further growth of the planetary embryos. You see here what happens in the system. The planets, as they start to grow, they start to migrate inwards. They form a chain of resonant bodies, but then there's a dynamical instability shortly after the gas disk phase that ejects some of the planets and also leads to some collisions. In the end, we have a system left of several inner supers. Additionally, what is interesting from these simulations, if you look at the inclination of these planets, you see initially the inclinations are pretty low because also the gas is not only responsible for the migration, but you can also damp eccentricities and inclination. But once the gas dissipates, you lose the damping effect, and you can have the collisions, and you see the inclinations and also the eccentricities increase. And in the end, you have a system left that has a few degrees of mutual inclinations between the planets, and that is actually very relevant for the comparison to the observations. So the first thing what I would like to mention here is like in this little cartoon. So if you have a flat system of planets where everything is in one, basically has no mutual inclinations, you could probably observe the full chain of planets with the transit methods. However, if the planets have small mutual orbital inclinations, you might actually only see one of the planets, even though the system contains several planets. You can actually play the same game within our own solar system that also has a few degrees of mutual inclination. And no matter where you would put a telescope, you could actually see a maximum of 3 planets transiting, and not 8 planets. And this is really just caused by the small mutual inclinations between the planets. So if we now compare our simulations to the Kepler observation, we see exactly that this effect is very, very important. So what we plot here is the cumulative distribution of our planets as the number of planets detected by transit. So the gray line that you see here, that corresponds to the Kepler planets, so the planets detected via the Kepler satellite. Now, if we look at the red solid lines, this corresponds to the number of planets that we have in our simulations from stable systems, where they do not undergo instabilities, and we have always our resonant chain with no basically mutual inclinations between the planets. The red dashed line corresponds to our simulations where we have instability, so where you have small mutual inclinations between the planets. The black lines, so the black solid line, corresponds to a synthetic detections. So basically, we take our systems and we run synthetic observations via the transit method to see how many of planets we would actually see from our simulations. And the solid black lines correspond to how many planets we would see from our simulations that had stable systems. And the black dashed line corresponds to the simulations where the detections of planets from simulations that went under instabilities. If we then have a mix between a stable and unstable systems, so the majority of the systems are unstable, we arrive at the green line, and that actually gives a quite nice match to the Kepler observations. So the idea here is really, you make our planets in the systems, and they all migrate towards the inner edge of the protoplanetary disk, where you could actually form a chain of resonant planets, but these chains then later break due to the gravitational interactions between the planets, resulting in a wider space systems and mutual inclined planets that actually allow to match the Kepler observations very nicely. To emphasize this point, we basically show here exactly the same plot, where now the different colors inside of each bars corresponds to the number of planets in our simulations for the system. So for example, if you have one planet that we could detect via the transit, the majority of our systems from our simulations actually predict that these systems should have 2 or 3 planets, so that there's hidden planets within the Kepler distribution where we only see one single transiting planet. The same trend continues if we go to higher and higher multiplicity systems. So our simulations predict that even if you see 1 or 2, maybe 2 transiting planets, there might actually be more planets hidden within that system. And this is also something that we want to test observationally, because if you do the follow-up observation of transiting systems with radial velocity method, we could of course detect the hidden planets that are not transiting. So I would like to come now to the composition of super-Earths. And I would like to start here with this plot from Zheng et al. From a couple of years ago, where they plot the planetary radius as a function of the planetary mass. These lines that you see here correspond to a certain compositions. So for example, the red line corresponds if you have a planet of a certain mass, and if the planet would be 100% made out of iron, what would be the radius of that planet? We can do the same thing, for example, for the blue line, which is the 100% water line. So if you had a body that is made 100% out of water, and you would have a 10 Earth mass body of that, you would have a radius of around 2.6 Earth radii. And you can, of course, mix these compositions very differently. So, for example, you also have here the line for a rocky composition. What you see here in this plot is of course, several things. So the first is, it seems that the small planets, the majority of the small planets, the small low mass planets, seem to be maybe from rocky composition, while you have a much larger variety of composition if you go to larger planetary masses. Of course, from this plot alone, it's very difficult to actually get the composition of the planet. Because, for example, if you look at planets that would lie directly on this 100% water line, it's of course very, very unlikely to make a planet that consists 100% of water. So you would actually have a mix of composition, but you still don't really know what is the exact mixture of these planets. So it's a very complicated business that might be actually, where we can actually break some of these degeneracies, maybe also with atmospheric characterization, maybe with James Webb later on. So instead, I would actually like to focus here on a bit more statistical and more simpler comparison. I would like to compare Rocky and Waterworld, which are both movies. One of them is better than the other, but I will not go into the detail of that. Okay, so the idea here is, if we look at the normalized fraction of the planetary radii of the observations, they actually observed a valley in the distribution. So the green line here corresponds to the Kepler observations. You see that there's a dip in the distribution here around 1.8 Earth radii. So you have less planets at a specific radius. And that is, of course, something that made us wonder, why is actually that? So what you can then do is you can take a look at the planets where you actually have accurate masses and radius distribution, and run interior models to actually see what the composition of those planets would be. You see here two different assumptions: if the planets would be made out of rock, or if the planets would be made out of ice. And what you see is that the position of the radius valley mostly corresponds to a rocky population. So that basically leads to the idea that the majority of these small mass planets are actually rocky in composition. And that, of course, has certain implications for our formation scenario. I would like to point out here first that, of course, this is only a statistical result. So it does not tell you anything about an individual planet, but you really have to look at each system individually. And it's also mostly relevant to up to like 100 days period, because the data becomes less good the further out you go. There's, of course, some debate now going on at the exact position and actually on the depletion of the valley, where there's a lot of the literature going on. And the position of the radius valley in itself is, of course, also very relevant, because it might actually tell you something more about the composition, that it might actually not necessarily be rocky, but might actually be a bit more icy. There's also some idea that you could explain this composition even if you have up to 20% water ice. So the takeaway point that I would like to make here is that there's a huge diversity in planetary compositions. So basically, you cannot assume that all super Earths are rocky or that all super Earths are icy. So you have to have a mixture. If you now paid attention to the model, to the movie that I was playing before, you actually saw that all of the planets had blue color, meaning they were all water rich. So there's a problem within this model that we actually have to address. The idea, one idea, of course, is that these mostly wet planets or water-rich planets could actually maybe actually explain the second peak of the population, but it can certainly not explain the inner rocky composition. So how can we actually make these planets rocky? So within the simulations that I've shown you, we actually made several tests how we can actually make the growth of these rocky planets happen. One idea is that we actually have larger pebbles in the inner disk. We originally started with millimeter particles, but if you have larger particles in the inner disk, you can extend the growth of the inner planets, and the outer planets might not outperform the growth of the inner planets. Additionally, it depends on the initial distribution of your planetary embryos, if they're all, of course, located exterior to the water ice line or not. So there's a lot of things that we can change. In addition, you can argue now about the sizes of the pebbles, if it's should correspond to the control sizes in the solar system or not. This was a debate that we faced during this work. Additionally, of course, if you start building your planets, maybe you could actually heat the planets. You could lose the water vapor. You can also think about what if the water ice that you would actually bring with the pebbles close to the planets might actually evaporate before you reach the planet, and you might actually not accrete the water-rich material. So there's a lot of things that we have to think about when we run these composition models. What I would like to point out here is that actually also the migration pathway of the planets in itself can actually influence the water, the content. You see here a so-called migration map, where the color coding gives you the direction of migration. So if you're above 0, you migrate outwards, and if you're below 0, you migrate inwards. And the red line here corresponds to the position of the water ice line. So if you're within this mass and orbital distance space, you migrate outwards, and if you're exterior to it, you migrate inwards, as indicated by the arrows. And this, of course, means for planets that grow close to the water ice line, it's very important if you would actually migrate inwards or outwards. You see here on the right a plot of two simulations where we plot the so-called growth track of the planet, so the semi-major axis and planetary mass. So the planet starts to grow, and if it can migrate outwards close to the water ice, and it stays in the outer disk and remains at the water-rich composition. If the planet, on the other hand, is allowed to migrate efficiently inwards, after it starts growing, it crosses the water ice line, and then it starts to accrete water poor material, and the water content of the planet changes. You see this here by the color bar. So initially, the planet is water rich. It crosses the ice line, it creates water poor material, and then becomes a planet with maybe only like 20% water in the material. So this means the migration pathway of the planet close to the water ice line is of crucial importance for the chemical composition of the planet. So this is something we have to take clearly into account within the simulations. Now I would like to talk a little bit how giant planets can actually influence the water content of sub-Neptunes. So the idea here is we start with a simple protoplanetary disk. We have here our central star, and you have our disk divided into two regions, interior or exterior to the water ice line. Exterior to the water ice line, you have dry gas and icy pebbles. But once the pebbles cross the water ice line, the ice can evaporate, and you can enrich the gas with water vapor. And you can also, of course, have planetesimals in the protoplanetary disk, either rocky planetesimals in the inner regions or also icy planetesimals in the outer regions, which I have not drawn for simplicity. We can now look at three different formation scenarios for giant planets and inner planets. So in the first formation scenario, so scenario A, we have a Jupiter planet that is exterior to the water ice line, and this planet reaches the pebble isolation mass, so it blocks the pebbles exterior to its orbit. So, but if the water-rich pebbles are blocked exterior to the planetary orbit, the inner disk cannot be enriched in water vapor anymore. So the water vapor diffuses inwards, and we are left with a dry disk. If then a sub-Neptune planets form, it would actually be, and it accretes a bit of gas from the protoplanetary disk, it would actually be dry and water poor. Now, in the second scenario, the giant planet would be located interior to the water ice line. So it still, of course, blocks the pebbles exterior to its orbit. But since the planet is interior to the water ice line, the icy part of the pebbles evaporates and can still enrich the disk in water vapor. And as a consequence, if you would then form a red sub-Neptune planet in the inner disk, the planet could actually accrete a water vapor from the protoplanetary disk and we have a small water content. In the third scenario is related to planet migration, so what I was talking to you before. The idea here is the planet forms in the outer regions of the protoplanetary disk where it can accrete a lot of icy material and then migrates to the very inner regions of the disk. And this would result in a very wet sub-Neptune. The difference here in the water content between scenario B and scenario C is actually quite large, because in scenario C, the whole planet actually can accrete a lot of water. So if you would have a classic 50-50 distribution between silicate and water, the planet formed here in this case would be 50% made out of water. While in the scenario B, only the atmosphere of the planet would accrete sufficient water. So the water content of this planet would be much smaller than the water content of scenario C. So you actually have an increasing water content of the sub-Neptune planets for the different scenarios. We can now link this to the observations of planetary systems where we have planets with inner planets and outer planets with determined masses and radii. And there's actually, unfortunately, not too many of those planetary systems. We found only like 15, 16 systems in the planetary database. And we plot here the planetary radius against the planetary mass of the inner planet. The lines, the colorful lines here correspond again to the interior model. So again, the red line corresponds to the pure iron line, and the blue line would be the pure water line. The purple line here corresponds to 1.8 Earth's radius. So this is the position of the radius valley that I talked to you about before. So the planets here additionally are also color-coded by the position of the outermost cold Jupiter in the planetary system. They are the Jupiter planets in the same system you see here, and this plot where we plot here the mass of the cold Jupiter versus the semi-major axis of the cold Jupiter. In addition, in this plot, we plot several positions of the water ice line. So in blue, this is the current day solar ice line position, and the cyan lines correspond to a protoplanetary disk model from Savido 2020, where we look at the position of the water ice line as a function of the disk's viscosity. So high viscosities mean that the disk has a lot of viscous heating, so the disk is very hot, so the water ice line is in the outer regions of the disk, while if you have a low viscosity, you have a low viscous heating and the water ice line is in the inner regions of the protoplanetaries. And you can now do a simple comparison where you can compare the position of the outermost giant to the position of the water ice line, and what would that then imply for the water content of the inner sub-Neptune. I would really like to stress here that, of course, here the timing of the formation of the giant planet is very important, because we assume implicitly that the giant planet forms before the inner super-Earth. The idea is that this is actually motivated from the solar system, where the idea is that Jupiter formed very early on to separate the carbonaceous and non-carbonaceous chondrites in the protoplanetaries. We can now take a look at the parameters from our simulations, where we plot here the different systems that we found in the database. We plot here for the different viscosities if the inner super-Earth should actually be water-rich or water-poor. And we see that for high viscosities, we predict that actually most of the planets would be water-rich. This is actually really caused by the really far out position of the water ice line. And as we decrease the viscosity more and more, the water ice line moves inwards, and we have more and more systems that could actually have enough systems that would be dry. We plot here in the last column the TSM, so the transition spectroscopy measurement, so to say, where the larger values indicate that it is easier to observe the planetary atmosphere. And in bold, we actually plot the systems that we could actually really characterize. So the sample is unfortunately very small. But the takeaway message here is that not only do the giant planets influence the water content of the inner planets, but actually, if we can determine the water content of the inner planets, we can actually constrain planet formation. Now I would like to come to the last part of my talk. What does the star tell us about the planet? The idea here is that that stars are very individual and have individual composition. So you see here a plot of the elemental abundance of different elements: carbon, oxygen, magnesium, silicate, as a function of the iron abundance, where 0 corresponds to the solar composition. So this is actually a log scale. If you would go to Fe/H1, it means you would be 10 times more enriched in iron compared to the sun. You first see that the lines for the different elements actually have different slopes, and this is actually caused by the different production side of the chemical elements through the galactic chemical evolution, because the elements are actually formed via different processes. Might be type 1, type 2 supernovae, and they happen on different timescales, so you have different levels of enrichment. We plot here on the right the C/O ratio of the stars in our sample as a function of the iron abundance, and the black line is the mean. And you see here, of course, there's a large scatter, so there's a large variation within the data. Nevertheless, we can actually ask the question, what does this actually mean for the chemical composition of the disk? Because the underlying assumption that we have is that the stellar composition could actually reflect the birth composition of the star disk system. So we can now take a look at the mass fraction of the elements of the molecules that we can form in this protoplanetary disk, depending on the abundance. We plot here the mass fraction of our different solids as a function of the host star metallicity, where we use a simple chemical partitioning modeling following the mean abundances as you see here from this plot. And what I would like to draw your attention to is the blue line, which is actually the water abundance. And you see here that the mass fraction of the water abundance actually decreases as Fe/H increases. And this is actually caused mainly by an increase in the C/O ratio, because if the C/O ratio increases, you have more carbon, and carbon actually binds oxygen very efficiently in CO and CO2. This means there's less oxygen available to make water. And this actually has a profound influence on the growth and composition of planets. So you see here again 3 different cross tracks, where we just take a look at 3 different compositions, where we have a high Fe/H our solar Fe over H and the low Fe over H. You see here that the planets, first of all, they actually grow a slightly different exterior to the water ice line, and then as the planets cross the water ice line, they actually can accrete again the rocky material and change their composition. You see this very dramatically for the planet forming this Fe over H minus 0.4. We are very water-rich exterior to the water ice line, but then the planet becomes actually a bit water poor, and you still have like 25–30% water ice. The important thing here to take away is that the change of the metallicity does not necessarily only change the growth of the planet, but it also changes the composition. You see here in the end, we have planets left for all three different simulations around 2 to 3 Earth masses, but the composition of these planets is very different. And this is not different because they started in a different position in the protoplanetary disk. This is really just different because the underlying stellar composition is different. So this is something that we really have to take into account in the future. So I think there's a clear indication that we have to go beyond the Fe over H for planet formation and composition, and also for the occurrence rates from observations. With this, I would like to summarize my talk. So the planet formation process is an interplay between accretion, migration, disk evolution, and instabilities. I think we can explain the Kepler observations quite well. But the composition is still something that gives us a little bit of a headache, and is something that we have to tackle within the next levels of planet formation theories. For the division between wet and rocky super Earths, I think the planet migration around the water ice line is critical for the water content of the systems. We also think that giant planets actually can really influence the water content of in a system. This is something that we can hopefully test by observations. And additionally, we should take into account that the varying stellar compositions can actually lead to varying water contents of the planets in itself. So when we look at the radius valley of the in the Kepler distribution, we should probably also look also at the underlying composition of the host star, but that could actually help to complicate the problem or maybe simplify it. With this, I thank you very much for your attention, and I'm happy to take any questions.
Many thanks, Bertram, for this nice overview. For the questions, you have two possibilities. Either you switch on your video and catch our attention, and then we will actually give you the word. Or you can also ask the question via the chat function, which is in the top right corner, this speech bubble. You press on that and you get to the chat function, and there you can actually ask the question. So I see Josep might want to ask a question. So if so, please go ahead.
I think you're muted.
Yourself.
Excuse me. Hi, Bertram. Really exciting talk. I was just saying. So thank you very much for this explanation. Well, many of us are looking for the pathways of water, not to terrestrial planets. So it's exciting that you make this progress. Particularly, well, it's quite exciting to know how your models are explaining the role that some of these giant planets can have as barriers of these, icy bodies, icy rich aggregates that were forming in the other part of the protoplanetary disk. I wonder if you are also considering the possibility to have another, sources of bodies in a slightly higher inclination. Like, for example, we have today the Jupiter family comets that are directly related, because of all these planetary perturbations with the other part of the main belt and how you think this can be fitting, no, in this model. Thank you.
Yes, thank you. That's a very excellent question, a very good point. So in the models that we're doing at the moment, we do not take the effect of planetesimals and how that could actually lead to the water enrichment of the inner systems into account. However, we know from the Earth that if, for example, if this process is really responsible for the water on the Earth, then the water enrichment is quite low compared to what we can actually get from the accretion of the gas, which can be enriched in the inner regions of the disk to like 10–20%. Also, if you would make the body entirely in the water-rich part of the disk. So it has an effect, absolutely. And it's something we have to take into account, especially if you look for habitable worlds, where you, of course, are much happier also with a smaller water content than what we are talking here about, but we do not take it into our model into account yet. It's certainly one of the next steps that we have to take a look at.
Okay, thank you. I have many others, but I prefer the others also ask. Perhaps later. Okay.
So, any more questions, please? You can either use, yeah, Eva, you might have a question, please.
Yes, thanks. It's very interesting talk. Thank you a lot, Bertram. And I mean, you mentioned, and in fact, you make a very strong point about the migration and connection rocky water. So it's very exciting part of the whole story. But I mean, as you know very well, I mean, there are quite difficulties to really know how the migration is going on, and there are quite a lot of in now development there. So what do you think is the best perspective in order to be able to sort of use this critical information about migration for the water content? How one should go around this? I mean, how to tackle the problem?
Yes, that's an excellent question. Of course, migration is a complicated issue where we are still trying to understand one of the processes, how it works. Especially if we now the idea goes to low viscosity disks, where we have a low viscosity, but then the migration might actually be different compared to disks with larger viscosities. So in the simulations that I've shown you, we use a large viscosity of alpha a few times 10⁻⁻3, where I think the migration prescriptions are actually quite okay, quite well. But of course, if you move to lower viscosities, things become a bit more uncertain because planets already at low masses start to open gaps and things become very messy. I also think there's one very crucial bottleneck in all these simulations, and that is the migration rates that normally come from the hydrodynamical simulations are normally derived for single planets. And we use here n-body simulations with many planets that all might disrupt the disk. And then, of course, we don't really know, is it okay to apply the migration rates from these simulations or not? So I think one way forward, of course, would be to use full hydro simulations to do this. But of course, it's very costly to really do this. So I don't really know if this really answered your question, but I think migration is still like a very important issue that we have to tackle from like a fundamental point to understand it better, especially in low viscosity disks, and then use it in these kind of models to see how that would actually change the composition of planets that we can form in these within these simulations.
Yeah, yes, thanks a lot for this discussion. That's what I wanted to hear. I mean, what is your view on how to proceed, and what are the difficulties, and what are the things to look forward? So, I mean, thanks a lot.
So I think studying migration is still very important.
Okay. Any other questions? More, please.
There is one question in the chat.
Yeah, let's look at it. Sorry. Yeah, Tim Lichtenberg asked a question. I was wondering if the iron to hydrogen ratio changes the water abundances via bridging of O in CO or CO2, why does this change the H2O abundance in between the H2O and CO2 ice lines? Or should this effect be limited to beyond the CO ice line?
Okay, so this effect is not limited to in between two ice lines. It's basically limited to the whole disk. So what we did is a chemical partitioning model, basically for the whole disk composition, and that then basically influences the water abundance for the whole disk. So it's not limited in between two ice lines. It's really limited for the whole disk in itself. Of course. We did a simple chemical partitioning model. So if you would run a chemical evolution model, things might of course also evolve in time, which we don't take into account here. But comparing it to chemical evolution models, for example, from EAI-Seminars, he actually agrees that if you increase the C over O ratio, you would have less water in these protoplanetary disks. So I guess this should answer the question that you have.
Hi, sorry,
Okay.
I could have asked the question myself eventually. Yeah, thanks. I don't know, maybe. So I in my understanding, the pebble stream inward, right? And so the water pebble, the water ice-rich pebbles just beyond the water snow line at any given point in time should come from just beyond the CO2 snow line.
Yes.
So when they decarbonize at the CO2 snow line, why? Yeah, I don't know. I'll have to look.
Okay. Now I think I understand your question.
Yeah.
So the problem is that the overall mass fraction of the water is lower, is reduced, because if you, let's say you start in the very outer part of the disk where everything is frozen out, then the mass fraction of the water is lower because you have more CO2 that basically where the carbon takes away the oxygen. But even as you then start losing the carbon, the CO2 as your pebble drifts inwards, the relative mass fraction in water is still smaller than what it would be if you would have an initially lower C over O ratio.
All right, thanks. Yeah.
I would also have like a question.
Sure.
Yeah. Okay. Perfect. Yeah. My question would be, if you take into consideration the late heavy bombardment, for example, for Earth. So like, how can I think about those water ratios? So like, is it bound in the mineral phase, or like, is there actually an ocean then up in a very wet sub-Neptune like world, or would it have been the Earth also the Earth we know without the late heavy bombardment, right? So like, would have there been oceans, or is it more bound in the mineral phase then afterwards?
You mean, sorry, I'm not entirely sure if I understand the question. You mean if you would build the planet exterior to the water ice line from just directly from the accretion of rock and water ice material, if that would then lead to a water world, or if the water would basically be trapped in the rocks and you would still not have a water world. Is this the question?
Exactly. Like, yeah, exactly. Is then the water world that the water is present but like bound in the mineral, for example, or is it then automatically like an ocean world? As you would
so I'm of course not an expert in interior structures and so on, but my assumption would be that you would actually then probably still have a water world kind of structure, because if the water fraction is initially high and it would correspond to like 20-30% of the mass fraction is in water, I don't think you can store that much water in the rocks.
Okay, so it would get released and then like form an ocean, for example.
Yes, that would be my naive guess.
Okay. Okay, thanks a lot.
Thank you.
Any more questions? Joseph, please.
Thank you. So I got another one, even going back to the primordial environment, because anyone that has been working on carbonaceous and ordinary chondrites knows, in particular, those that are really type 3, very pristine chondrites. So this this dichotomy between, you know, low FeO and high FeO chondrules, you know. Well, basically, the thing is that the primordial chemistry was a mafic silicates, magnesium-rich mafic silicates, like they are usually forming comets, cometary silicates. But it seems that over time, the protoplanetary disk was enriched in oxygen in vapor phase. You know, so you have an increasing, as you are heating the condules that were magnesium-rich condules at the very beginning. You have probably vaporization, so a huge amount of oxygen and iron are going to the vapor phase, and then over time, at least the general, you know, theories are proposing that there is this increasing FeO, the incorporation of iron oxide into this, the mafic silicates, you know, so you are increasing the magnesium oxygen silicates into iron oxide, you know. Do you think that at some point you can claim that these changes that can be made by the formation of giant planets and the migration of these giant planets can get some clues about how this can happen, you know, because perhaps when you have a planet that is a barrier, you are avoiding that huge amount of water is migrating inwards. So at that point, even perhaps at the beginning of, you have less water in the inner solar system, and then when something happens and migration is promoting, you know, migration inwards of this water ice, you increase the level of oxygen in the environment, and then you can form iron oxides that incorporate into the silicates in the vapor phase. Do you think that this can be somehow explained by your models, or you were considering other ways to enrich these the silicates, the structures of the planetesimals?
So, that's a very good question. We have not looked into details into for solar system compositions within this model. I mean, the paper from Morbidelli et al. 2016, it basically deals with the scenario that I presented for the sub-Neptune planets for the solar system. So basically, the idea is Jupiter grow and it blocked the water vapor, the water-rich pebbles to go into the inner system. So you can certainly influence the water content by this mechanism. Another idea that was actually put forward regarding this is, of course, the heating with aluminium-26, where you then could basically evaporate the water away from your planetesimals. So I think there are several ways how you can do this, but I'm not a full expert within these simulations.
Sure.
But certainly the giant planets have a profound influence on the material interior to their orbit, depending, of course, when they form and how fast they form.
Okay, thank you. If you can share with us your email in the chat or wherever, perhaps I contact you back concerning
Sure.
some of these topics. Thank you.
Oh, absolutely.
Okay. If there are no more questions, I would like to conclude this seminar, and I would like to invite you for next week, where we've got another speaker from the Max Planck Institute of Astronomy, which is one of our participating institutions, namely Bertram, who has also recently joined the institute. With that, I would wish you a very nice evening and hope to see you again in 2 weeks. Many thanks.